All right, so we left off last time looking at the formulas for adding, subtracting, scaling, and finding magnitude, all without doing any sketches. Okay, so we went through all those formulas. Another thing we're going to look at is how we can take a vector that's not a unit vector and turn it into a unit vector. Okay, just a reminder, if you don't remember, unit vector means that it is 1 unit long. All right. If a vector is not a unit vector, we can scale it. If it's too short, we can make it a little bit longer. Or if it's too long, we can make it shorter. The goal is to turn a vector into a unit vector. Kind of like this picture. Pretend that that vector in black was like 5 units long. The vector in red has been scaled down to point the same way, but it's 1 unit long. So that's the goal. Scale it to be 1 unit. So let's see if we can come up with kind of a pattern of what you have to scale a vector by to make it 1 unit long. So let's say we had, I'm going to use the word magnitude, and the scale factor. If you had a vector that is 5 units long, what would you scale it by to make it 1 unit? Yep? 1/5. And it's important to try to see the pattern in the numbers that come up here. All right, 1/5. What if you had a vector 8 units long? You would scale it by 1/8. What if you had a vector that was 1/3 of a unit?
3.
You would scale it by 3. Okay. So what if you had a vector that was x units long?
X negative 1.
Okay, x to the negative 1 or
1 over X.
1 over x. So if you scale a vector by the reciprocal of its length, you will always turn it into being 1 unit long. Okay, that's the pattern. So let's write that down. So to find a unit vector, if I give you a vector, you're going to be finding a new vector that points in the same direction as the original, but it's going to be scaled to 1 unit long. All right, so now we just have to figure out how to write that as a formula. So let's say you had a vector v. If you want to scale it by the reciprocal of its magnitude, you're going to multiply by something in front. Since it's a reciprocal, it's going to be a fraction. How do we represent the length of a vector? Because that's what I need to put in the front here, the reciprocal of the length. How would we write that? How about if we start with just the length? What's the symbol we use for length of a vector?
2 lines and the V.
The two double bars around the V. So how would you write the reciprocal of that?
2 bars and then 1 over V.
1 over, yeah. That's how you write the reciprocal of the length. Or if you want to put it all together as one fraction, you can think of like multiplying straight across. 1 times v is v, and the magnitude is in the bottom. All right, so that's how you can turn any vector into a unit vector. So the first step to finding a unit vector is to look at the vector that you have and find the length. If the length is 1, you're done. There's nothing to do. If the length is not 1, scale it to make it 1. Okay, so let's try this one. It says find the unit vector for the vector 3i minus 4j. All right. So what's the first thing that I need to figure out about 3I minus 4j?
If it's 1 unit.
Yeah, let's figure out how long it is, and then we'll go from there. Can someone remind me from yesterday? It's the, I think, the very last problem we did. How do I find the magnitude of vector v?
Take the square root of 3 squared minus 4 or plus 4 squared.
Right, Pythagorean theorem. Square root of 3 squared plus 4 squared. And that's going to give me a magnitude of
5.
5. Okay. So now I can answer the question, is that a unit vector?
No.
No. We need to make it a unit vector. So, to make v into a unit vector, what do I scale it by? 1/5. So now I want to know what is 1/5 v. Okay, and remember, to scale a vector, you distribute your scalar to each component. So originally the I component was 3. When you scale it, what will it become? 3/5. Okay. The J component was -4. When we scale that, it will become
Negative 4/5.
-4/5. So there is a new vector pointing exactly in the same direction as the original, but instead of being 5 units long, we forced it to be 1 unit long. Okay. So any question on finding a unit vector from a given vector? Yes?
Where do you get the 3/5 and 4/5 from? Sorry.
So that's when you distribute out 1/5 to each component in vector v. The 3 and the -4. Okay, that was the first thing. And the last thing we're going to do in this part of the lesson is an application to velocity. So when we write something as a vector, it needs to be written as a number with I and then a number with J. Right, I'm going to show you how you can convert information in a word problem into that format. So a velocity vector does 2 things. First of all, it describes the speed that the object is moving at, and it describes the direction. How do you think we're going to describe direction? What do we use in math a lot to describe the direction of something? Yeah?
Arrow?
Degrees.
We use an angle. So we're going to know some kind of angle that the object is thrown at. And we're going to know the speed that the object is thrown at. But those 2 pieces of information are not the vector. It's the speed the object is going at an angle. So we got to break that up into a vector. So how are we going to do that? Okay. So let's say theta is going to represent the angle the object is thrown at. Now, I know the object would normally start to curve because it's going to come back down. But we're going to pretend we're in outer space with no gravity. So when you throw it, it just keeps going. It never stops. All right. When we write something as a vector, there's 2 components to it. And this was a question in the homework. What are the names of the 2 components? The blank component and the blank component. Yeah?
The horizontal and vertical.
The horizontal and the vertical. So what we need to do is visually represent the horizontal and the vertical. And the way you can do that is just take a vertical line. It's bigger than I need, but put it right there. And that allows me to break it up. That is the horizontal, and that is the vertical. I'm going to let the length of the horizontal be the letter x. the distance from there to there. And I'm going to let y be the length of the blue arrow. Just to be clear about that, the x and the y is not the arrow itself. It's the length of the arrow. Where the v, with the arrow on top, that's actually the physical arrow itself. That's the vector. All right. So what we have to do is see if we can break that up into the horizontal and vertical components. The value for x is going to go in that box. The value for y is going to go in that box. We need to figure out how to get the x and the y if you're given this and that. Okay, let's start with x. What do you think we're going to use? And we've done this a few times before. That's going to help us to relate those three things. Sine and cosine. Which one would we use for x?
Cosine.
Cosine. Can someone remind me, what's the definition of cosine again?
Adjacent over hypotenuse.
And can you be more specific about what do you mean adjacent over hypotenuse?
X over, it would be,
Like I'm thinking, what do you mean by, when you say the word adjacent, can you describe
The
that?
leg- The leg that is touching the angle, or adjacent to the angle.
And what about that leg? Like the color of it? How heavy it is?
the
The
length.
length.
The length of it, that's important. It's the length of the adjacent over the length of the hypotenuse. Okay, what's the length of the adjacent? The length of the adjacent is x, yes. Now, what is the length of the hypotenuse?
V.
No, v is the vector of the hypotenuse.
Oh no.
How do we write the length of v?
Oh no. X squared, or,
Actually, probably.
Uh,
Two line.
How do we do it? Kind of.
isn't it X, it's X squared.
No, you're closer.
Yeah.
Two lines via.
Yeah, so it's not just a single, like the double
Yeah,
bars.
that. Mhm.
Yeah.
Weird.
That's the formula for cosine of theta. The length of the adjacent over the length of the hypotenuse. And now let's solve for x, and that's what goes in this box. How would you get x by itself?
Multiply by the bottom.
Yep, multiply by the magnitude of v. So what would be in that box?
And the magnitude of v times cosine theta.
Magnitude of v cosine theta. That's what goes right here. That is the horizontal component of your velocity vector. Magnitude v cosine theta. And we put an I next to it, so we know that that's the horizontal. Now we need the vertical. Horizontal, vertical. And that's going to have a J. But we got to put what goes on the underline. Okay, what trig function would relate this, that, and that?
Sine.
Sine? And what would the sine of theta equal?
Y over, the, like V with the two lines next to it.
Magnitude of v.
Magnitude of v. All right, so length of opposite over length of hypotenuse. And that means the y, which is the vertical component, which goes in that box. What would be the formula for y?
The magnitude of V sine theta.
Yes. Magnitude of v sine theta. So that is the formula for a velocity vector. It takes an object that's traveling at a certain speed and angle and breaks that speed and angle into two parts, the vertical component and the horizontal component. If you want to think about it in terms of a triangle, it's the base of the triangle and the height of the triangle. That's all it is, base and height. So hypotenuse cosine is always the base, hypotenuse sine is always the height. Any question on that formula? Okay, so now I'll give you a problem with a radius, with a velocity and an angle, and we're going to convert it into a velocity vector. But you need that formula to do it. Let me label what these are, because I was going to do that on the next page, but let me do it right here. That is the initial speed. The magnitude of v. Think of what magnitude means with velocity. It's speed. How fast is the object going? Same for this one. Same thing. The angle is, it's the angle the object is thrown at. That's usually an angle relative to the ground. So if you threw something at a 90-degree angle to the ground, that's straight up. If you threw something at a 45-degree angle, it's halfway between horizontal and vertical. If you threw something at a 0-degree angle, then that's perfectly horizontal in front of you. Okay. So it's the angle the object is thrown at. And remember, we're in outer space, so the angle, once you throw it, just keeps going. Doesn't come back down. If it came back down, well, some things are a little different. Okay, so here's our problem. It says we're throwing an object at 50 miles an hour at an angle of 30 degrees. Find the velocity vector. Write your answer in unit vector form, which is exactly the formula I gave you. And then once you get your answer, explain what it means. Okay. So you're going to have a horizontal component, vertical. Okay. What's the formula when I fill in my initial speed and my angle for the part that goes in front of I?
50 cosine 30 degrees I.
And what's the formula for the part that goes in front of J?
50 sine 30 degrees J.
Yep. So what you've just done is you had something going at a 30-degree angle, like that. The speed of it is 50. And you broke it up into that green and that blue. That's what we just did. Just broke it up. Okay, let's do it out and see what we get. On a calculator. Calculator would be great. Let's see what we get. All right, so 50 cosine 30, 50 cosine 30. Check your in degrees, you're good. That's 43.3 I plus 50 sine 30 is 25. So it's 25J. Right, so that's the vector that represents that velocity in the problem. Now it says to explain the meaning of each component. Well, how many components are there?
2.
2. What is that 43.3?
Horizontal.
Yeah, the horizontal
Horizontal,
length, or the horizontal length.
it's not the horizontal
Horizontal
length.
magnitude.
And what does that mean in this problem? It's the horizontal, yeah?
Distance.
No, it's not a
Horizontal
distance.
velocity.
What about the velocity? Velocity
Is
has
the
two
speed is
parts.
going in the horizontal direction?
The what?
The velocity in the horizontal direction?
Yes, it's the speed of the object horizontally. What is that? If you were standing in front of this object and you had like a radar gun and you pointed it right at the object coming at you, it would say it's coming at you at 43.3 miles an hour. It wouldn't say 50. The reason it wouldn't say 50 is because if you're standing on the ground and the ball was thrown up at a 30-degree angle, some of the velocity is going into upward speed. It's not all in going into horizontal speed. The only way that all the speed would go into horizontal is if you threw the ball at a 0-degree angle. And that's pretty much how a pitcher pitches like in baseball. They throw it at a 0-degree angle because they don't want to throw the ball like, lob it in like that. They want to throw it straight. Okay, so that might be a little bit of an angle, but not much. It's pretty much a straight line. Okay, so that's the speed in the horizontal direction. And what about the 25?
The speed of the object in the vertical direction.
Right, that's the speed of the object in the vertical direction when it leaves your hand. So remember, we're in space. So if you were above this situation and the object was below you and you looked down at it, the object would be coming up at you at 25 miles an hour. Okay? That's the speed it would be coming upward. So it's the speed in vertical direction. Any question on that? All right, so that's how you convert a velocity vector into a, velocity word problem into a velocity vector. So we've looked at two main operations that we can do with a vector and a vector. We've added a vector to a vector. We've subtracted a vector from a vector. And you say, well, we did multiplication. No, we didn't multiply a vector and a vector. We did this. We did a number and a vector. What did we call that?
Scalar.
Scalar. That's called a scalar product. You're taking a number times a vector. Well, now we're going to do a vector times a vector. Okay? And this is called a dot product. When you multiply a vector times a vector, first thing to understand, there's actually two ways to do it. There's one way that's called a dot product. There's another way called a cross product. We're not doing cross product yet. Okay, that's maybe tomorrow. Depends. But we're looking at what's called a dot product. When you are doing 2D vectors, this is the only way you can multiply two vectors together. Cross product does not exist in 2D. You have to have 3D to do it. Okay. So let's suppose that we had those two vectors. Each vector has its own horizontal components, A1 and A2, and each vector has its own vertical components, B1 and B2. When we do an actual problem, all four of those are going to be numbers. A1, B1, A2, B2. Okay, kind of like, I think I have an example down here. Yeah, like that. Okay, all those numbers in front of the I's and J's, they'll be numbers, not letters. So now I'm going to show you the formula for finding a dot product. It's going to involve these four things that I just circled. Those are the four things you use in the formula. Okay, it's a very simple formula. All you have to do to find the dot product is take A1, A2, multiply them together. Take B1, B2, multiply those together. And then add the results. That's how you find the dot product. So what I want to think about is what kind of answer do we get when we're done? A1 and A2 are just numbers. What do you get if you multiply a number times a number? You just get a number. What about if you do another number times another number? You get another number. And what if you add a number to a number? You get a number. So the point is, when you do a dot product, the answer is just a number, like 7, -6, 12.4. Okay? Just a number. That number means something, but I'll tell you later what the number means. Okay. So let's see if we can find the dot product between V and W. So the first thing I do is I set it up just like the formula up above. Just like that. And let's try to make sure we follow exactly the pattern we see in the formula when we do this problem. Okay. What would go in my first 2 sets of parentheses? Yeah. 2 and what?
2 and then 5.
2 and then 5. Yep. So it's going to be 2 times 5 plus what's going to go in the last 2?
Would it be -3? Or just -3 and 3?
-3 and 3. Yep. So 2 times 5, -3 times 3. 2 times 5 is going to give me how much?
10.
10. And -3 times 3 gives me?
-9.
-9. So that gives me a dot product of 1. Yep. That is the dot product between V and W. 1. Again, later I'm going to tell you what that 1 is used for. It does something. Now let's try W dot V.
Wouldn't it be the same?
Well, let's write it out, and I want to make sure we follow the formula exactly. And then we'll see if it does come out the same. What would go in each parenthesis this time? 5 and then 2.
And then 3 and -3.
And 3 and -3. So what ends up happening is when you do W dot V, the order switches, but
It's going to be the same.
it still comes out the same. Because you can switch the order and it comes out the same, what do you think that means about the dot product?
It's commutative.
It is commutative. It doesn't prove it's commutative. It means it works that one time. But I will tell you it works all the time. Okay, the dot product is commutative. Okay, let's try one more dot product. V dot V. So we're dotting the vector V with itself. Another thing I should mention, but I just kind of skipped over. When you write multiplication, you have to use a dot. You have to, right? You cannot put any other symbol between those 2 vectors and have it mean dot product. If you put this, that means nothing. That's nothing, right? That's, I don't know what that is, it's nothing, right? If you put this, that's called a cross product, when you put the little x between them. So the symbol you use for multiplication is picky in this part, because it's a dot product, so you have to use a dot. If it was a cross product, you would use an x. But those are the only 2 symbols you can use, and we haven't talked about this one yet, so don't worry about it. But I should mention that. All right, so V dot V. How am I going to set that one up?
2, and then negative 3,
So 2, 2, it's the same number twice, and then plus
3 times
negative 3 and negative 3. Okay, so what's the dot product of V with itself?
-5.
13.
So yeah, 2 times 2 gives you 4. Negative 3 times negative 3 gives you 9. And then when you add them up, you get 13. So that's V dot. Any question on finding the dot product? Okay. Let's try example 2. It's the vector 2, 6 dotted with the vector 0, 0. What's going to be the dot product here?
0.
0 the number or 0 the vector?
0 the number.
0 the number, right? Anytime you do a dot product, the answer is always a number. So when you write the answer to this, it is 0 the number. Okay, it's not a bold 0. It's not a 0 with an arrow on top. It's just the number 0. And when you get a dot product of 0, that is something special. So we'll look at what that means in a minute. If you get a dot product of anything other than 0, it's not as special for what I'm thinking of. Any question on that? Okay, so distributive property works with dot product. That is something you are allowed to do. So if you had 2 vectors added together and you wanted to find the dot product of that sum with you, you can do it 2 different ways. You could add the 2 vectors together first, and then you could do the dot product. Or you could do the dot product separately with each vector, and then add the results when you're done. So you can either do dot product first and then add, or you can add and then do dot product. That's distributive property. You can do it either way. Now, the last thing we're going to look at is what can you use the dot product to do. So if I had 2 vectors, let's say one like that and one like that, what would it be just amazingly cool if we knew how to do? Like if you know how to do this, like everyone would think you're the greatest.
The effort.
So they're vectors. We don't really have such thing as like an average of them. We already know how to add them. We know how to subtract them. Yeah? All right, it kind of has something to do with, well, when you rotate, how would you specify how much you would rotate it by? By an angle. So it would be really cool if we knew how to find that angle right there. Wouldn't it? I mean, you'd be able to sleep better. You wouldn't have to worry about it. You'd know how to find it. Well, I'm going to show you how to find that angle anyway. So when we talk about finding the angle between 2 vectors, we're talking about the angle that's between them. Technically, you have one inside, but you also have this angle on the outside. We're talking about the one on the inside. Okay, that's the smaller angle. To find the angle between 2 vectors, you have to do 3 calculations. And all calculations we know how to do. The first part of the calculation is the dot product. You need the dot product of your 2 vectors. The other thing you need is the magnitude of each vector. If you have these 3 pieces of information, dot product and the product of the magnitudes, you can figure out the angle between your two vectors. So it's cosine theta equals dot product over the product of the magnitudes. And the reason why it has cosine is because this formula comes from the law of cosines. It's not that hard to show you where it comes from. It's not something I'm going to go through right now. At least, I'm not going to go through the whole proof of it. But you've got those two vectors. If I drew in the third side, what shape do I have now? I have a triangle. Okay? And because these two original vectors were given to me, would I be able to figure out the length of this side? If this vector was given to me with numbers.
Yep.
Yeah. How about the length of this bottom side?
Yes.
Yeah. And if you know the length of these two sides, you must know where each side starts and stops. Well, if you know where it starts and stops, you can also get that third side. If you knew all three sides, what kind of triangle do we call that when you know all three sides? We call it side, side, side. And when you have a side, side, side triangle, if you want to figure out something that you don't know, you have to use the law of cosines. And the thing that we're figuring out that we don't know is that angle right there. So we're basically using law of cosines to solve for one angle in this triangle. Everything always comes back to triangles, pretty much. But this formula is a lot shorter than the law of cosines. If you remember, law of cosines was this whole long thing. Okay, add all that in it. What we've got is a lot shorter. And that's because of the way it works with vectors. It shortens up. Okay, but we're not going to go through that. Okay, does everybody have that formula? All right, so now let's try to find the angle between the two vectors. Which, if you ever forgot the formula, you could do it with law of cosines. It's going to take you a long time. Right? It's going to be a lot longer to find the magnitude of that, find the magnitude of that, find the magnitude of that, and then fill all the letters in, and then solve for your angle. That's going to take a while. All right, let's not look at that yet. Let's do this. So example 3. Find the angle between 4i minus 3j and 2i plus 5j. Well, let's graph them and see if we can look at them and get an idea of what they look like. And then we'll find the angle and see if it actually matches up with our picture. So 4i minus 3j. Okay, let's use this grid. Okay, so we've got right 4, down 3. So let's draw that vector. 1, 2, 3, 4. 1, 2, 3. That's roughly 4i minus 3j. Okay, the next one is right 2, up 5. Right 2, up 5. So I'd say about like that. Okay, if we look at that angle, about how big do you think that angle is? Yeah, it's a little bit over 90. It's not 90. If it was 90, it would be like an L shape. It's a little bit more than 90, maybe 95, 100, somewhere around there. So let's find the angle and see if it comes out to a little bit more than 90. All right. So first thing we need is the dot product. Can someone give me the calculation to find the dot product?
2 plus -3 times 5.
4 times 2 plus -3 times 5. And that's going to give me a dot product of 8 minus 15. Dot product can come out negative. That's fine. What's 8 minus 15?
8 minus 15?
Yeah.
Negative
That's
7.
negative.
Okay, so we get a dot product of -7. Can somebody else tell me how I set up the magnitude of u? Somebody different. You're doing great. Yeah?
The square root of 4 squared times 3 squared? Or
Square root of 4 squared
Oh, not times, plus.
plus
3 squared, -3 squared. It's
-3 squared.
kind of more positive
Okay.
anyway.
And what's that going to give me for a magnitude?
That'll be 16 plus 9, which would be calculator.
Square root of 25, which is 5.
Just 5.
Yay.
Square root of how much?
25, which is 5.
Which is 5.
We did it for
Okay.
me.
So we got the magnitude of u, and can someone else tell me how to get the magnitude of v?
It's 2 squared plus 5 squared.
Said-
Under a square root.
What?
Square root of 2 squared plus 5 squared.
2 squared plus 5 squared, and that's going to give me how much?
Square root of 29.
Square root of 29. Okay, so I got all the pieces of information I need to find the angle. What trig function was this formula equal to?
Cosine.
Cosine, because it comes from law of cosines. So, cosine theta equals, and what was in the top?
U times V. So
Can you say that again?
U times V, which is -7.
Dot B.
U dot B.
U dot
Yeah.
B.
So the dot product is in the top. And what's in the bottom?
5 times square root of 29.
The product of the magnitudes. 5 root 29. Now, that's not the angle, that's the cosine of your angle. So how are we going to get just our angle?
Take the inverse cosine of both sides.
Yep. Just like you would in law of cosines. Take the inverse cosine of each side. And remember, we're looking for an angle between probably 90 and 100, somewhere around there. Okay, so we get inverse cosine of -7 divided by, I would put this in parentheses. If you don't, it will mess up. Or the person typing it could mess up too. Okay, that's exactly how I would type it in. Inverse cosine of -7 over 5 root 29. And yeah, it's more than 90. We said 95, 100. It's 105. Yeah, that's right in the area we thought. So it's 105.07. 2 decimal places is generally what you're going to want to do. Okay. Any question how we got the angle between 2 vectors? All right, so now, still talking about the angle. There is a special angle that could happen between 2 vectors. 105.07, that's not special. That's just random angle. Anybody have an idea what would be maybe considered a special angle?
0.
A 0-degree angle would be special. Yep.
180.
What is it?
180.
A 0 and a 180 would be the same case. They're both special. Yep, we're going to talk about both of those.
90.
And 90 is the other one. So if 2 vectors have an angle of 90 degrees between them, they are perpendicular. When we talk about vectors being perpendicular, that's the word we use. Anyone think they know how to say that?
Orthogonal.
What is it?
Orthogonal.
Orthogonal. Yep, it's orthogonal. So orthogonal means perpendicular. Why do they use that word when they talk about vectors? I don't know. But they decide to use a different word. It just means the angle is 90 degrees. So let's think about that for a second. Your formula to find an angle is the dot product over the product of the magnitudes. Let's say that you already knew the angle was 90 degrees. Let's fill in a 90 right here. And we don't know any of the other stuff. Okay? We just know that we have an angle of 90 degrees between two vectors. Any vectors you want that are perpendicular. If they were perpendicular or orthogonal, that would be a 90. The rest of it, I don't know. Just leave it. Let's do out the cosine of 90 and see what we get. Okay, cosine of 90 is 0. So if two vectors are orthogonal, then the entire left-hand side comes out to 0. 0 equals this over that. But it doesn't really matter exactly what's in the top or in the bottom, because I'm going to block those things out for now. As I said, I'm going to block those things out like that and like that. It doesn't matter what's in the top or the bottom. Just look at what you have. A fraction equal to 0. How can a fraction ever come out to 0?
If the top is equal to 0.
If the top is 0. The top has to be 0 for this entire fraction to equal 0. And in this case, what's in the top is the dot product. So when you are finding the dot product, if the dot product comes out to 0, it would make this entire fraction 0, which means this side would equal 0. And if that's 0, the only way to get a 0 there is if you take the cosine of 90. And if you filled in 90, then that means the vectors are perpendicular. Right? So that is a shortcut you can use to figure out if two vectors are orthogonal. The dot product has to come out to 0. It is the only way you can make that fraction 0. And that's what has to happen if they're perpendicular. The fraction has to be 0. So now, this is asking, are the following vectors orthogonal or perpendicular? Same. Okay. I only need to find one thing to answer that question.
The dot product.
I need the dot product. That's all I need. It doesn't say if they're not perpendicular, find the angle. It doesn't say that. So all I need to do is find the dot product, and then I can answer yes or no. Okay. What's going to be the calculation for the dot product?
2 times 1 plus 1 times 2.
2 times 1 plus 1 times 2. That's a dot product of how much? 4. So are those vectors orthogonal? No. Because it doesn't matter what you have in the bottom. If you put a 4 in the top, 4 divided by anything will never come out to 0. And if it doesn't come out to 0, then that's not a 90. And if that's not a 90, then they're not perpendicular. What could you do if you could just change one thing? Just change one thing and make those vectors perpendicular.
Make one of them a negative.
Yeah, you can make anything a negative. Either make any 4 of those spots, make one of them a negative, and they will be perpendicular. Yep. Okay, so nice shortcut for perpendicular. What were the other two angles people said?
0 and 180.
0 and 180. What kind of vectors do you think you would have if they had a 0-degree angle or a 180-degree angle?
They point in the same direction or directly opposite.
They would either point in the same direction or directly opposite. So we could consider those kind of vectors to be what? The two vectors that point in the same direction, but not right on top of each other.
Parallel.
Parallel. Yeah. So two vectors that point in the same direction, you could think of that as a 0-degree angle, because if you line them up, they'd be right on top of each other. Two vectors like this are also parallel, but it's because they point in opposite directions. And if you were to line those vectors up, they would look like this. That's a 180-degree angle. And if you line those up, I can't really show you, it would just be one on top of the other. And that's a 0-degree angle. Okay. So we got that. So two vectors are parallel if they have an angle of 0 or 180. So let's see if we can figure out if there's a shortcut for parallel, or if we just have to do the whole thing. Okay. So one way they could be parallel is if the angle was, let's do the 180 first. Let's say we don't actually know what our vectors are, we just know they're parallel. You'd have the dot product in the top, and the product of the magnitudes in the bottom. Again, I don't know what they are, but I know they're parallel. If I do the cosine of 180, what do I get?
-1.
Cosine of 180 is -1. And you have your dot product and your product of your magnitudes. How can a fraction equal -1?
Top and bottom are equal.
If the top is a negative or the top and bottom are negatives.
Same value, and except one of them is negative.
What do we call numbers with the same value and one's negative?
Right there. Inverse? No, that's
No, not inverse. It's not a super fancy word.
opposite.
Opposite, yeah. Opposites. Right? Two numbers that have the same value, but one of them is negative. If you divide opposites, you will get -1. Well, that means in order to know if the top and the bottom are opposites, you need to know the top and you need to know the bottom. You have to know both. So there really isn't a nice shortcut like perpendicular. Okay? To figure out if two things are opposites, you need to know both of them. So you're going to have to find this, and then you're going to have to find that separate. Right? How about the other case for parallel? Would be 0-degree angle. You'd have your dot product, product of your magnitudes. What's the cosine of 0?
Isn't it 1?
1. How can a fraction come out to the number 1?
The top and the bottom are both positive. And
If they're the same.
If they're the
if
same.
they're the
Yeah.
So, in other words, the top and the bottom have to be the same, but to know if two things are the same, you have to know the top one, and you have to know the bottom one. You have to know both. So, no, there is no real shortcut for this. So let's see if we can figure out, for the last question, if these two vectors are parallel. I mean, I guess there's a little bit of a shortcut. You don't have to do the inverse cosine. If the top and the bottom come out the same, then you're done. But you still have to find the top and you still have to find the bottom. Okay. What goes in the top? In general, the dot product. How are we going to get the dot product here?
you would do 4 times 2 plus
Say that one more time.
4 times 20
4 times 20
plus -5 times -25.
plus -5, -25. Okay, 4 times 20 gives me
80.
80, and negative 5 times negative 25.
125.
And add the two together, and we get
5.
205.
05.
Well, there's one thing I can say right away. We know that these vectors are not what?
Parallel.
They're not perpendicular.
They are not perpendicular. Do I know if they're parallel? No. But I know they're not perpendicular because I would have had to have gotten 0. Okay, so we got to keep going. How do we get the magnitude of V? Calvin, how do I get the magnitude of V?
You do the square root of 4 squared plus negative 5 squared.
Square root of 16 plus 25, which gives me square root of 41. Okay, I got magnitude V. And last thing I need is magnitude of W. Braden, how do I get the magnitude of W?
Square root of 20 plus negative 25. Square root.
Say it one more time.
It would be 20 plus negative 25.
Not quite.
20 squared is negative 25 squared.
20 squared plus negative 25 squared. So we just got to remember to square them. And that adds up to how much?
125.
So it's the square root of 1,025. Okay. So what's in the top here? Which number?
205.
This is in the top. And what's in the bottom?
Square root of 41 times square root of 1,025.
Right. The product of those two in the purple box are in the bottom. If these are perpendicular, then what would the product of those two numbers have to come out to?
205.
It would have to come out to 205. Right? It's not going to come out to negative 205 because it's a positive times a positive. So let's see if the bottom comes out to 205. So square root of 41 times square root of 1,025. 205. So now we know the bottom number is 205, the top number is 205. What does that mean?
They're perpendicular. Well, that equals 1.
They're parallel.
They're parallel.
Yeah.
Yeah. So the answer to here, determine if they are parallel. Yes. These are parallel. Are they parallel because the angle between them is 0 or because the angle between them is 180?
It's 0.
It's 0 because it came out to 1 when you divide them. Okay. So essentially you've got two vectors that look like this. Two vectors pointing the same way. One of them's longer or shorter, but that is considered parallel. Okay. Question on that? All right. So that is dot product. Okay. So on page 352, 7 to 17 odds. Each question has 3 parts. First part is, I think, find the dot product. The second part is find the angle. And then the third part is, are they parallel, perpendicular, or neither? So that's from the dot product. And then the stuff we covered right before that was 56. So it's 7 through 17 odd, and then those 5 questions at the bottom. Okay, so we'll take a look at that tomorrow. I'll be after school tomorrow if anyone needs extra help. And we'll finish our last section for the week.